Sí. Bueno, bienvenidos al Seminario del Departamento de Geociencias. Hoy tengo el gusto vamos a tener dos charlas. Marín Denolle, ¿no? De la Lipovsky, profesores en la Universidad de Washington. Este verano estuve ya visitándolos un rato. Marín, trabajamos con Marín que con Brad. Con ambos hemos publicado algunas cosas. Marín hizo su pregrado y su maestría en el normal del país y se fue a hacer el doctorado en Stanford.
2009.
Entonces, sé bastante. Yo era postdoc ahí, entonces trabajamos mucho en los aspectos. Lo que van a notar es que nosotros trabajamos el desarrollo sísmico para mirar la amplificación en las ondas en cuencas sedimentarias y cosas por el estilo. Lo que van a ver acá es completamente diferente, eso muestra la los diferentes temas que ha trabajado Marín desde su doctorado. Es una de las mejores sismólogas que hay en el mundo, pero pues trabajan miles de cosas con Entonces hoy hay dos cosas importantes. Uno, inteligencia artificial, y dos, unas nuevas tecnologías que están saliendo y utilizan, digamos, DAS, que es usar cables de fibra óptica para hacer sismología. Ya escucharemos al respecto. ¿Bien? Gracias.
Muchas gracias, Román. Hablo español, perdóname. Lo siento. Today I will discuss with you how artificial intelligence can help us understand and forecast geohazards. And let me first explain what I mean by geohazards. I think a lot about geohazard as a geophysicist beyond earthquakes. The one geohazard that is very important, especially in Western United States, are the wildfires. And recently, there was very drastic wildfire in California that had a huge damage cost and killed a lot of people in Los Angeles. Closer to you, I think you can think about geohazard or you associate geohazard with landslides. And we traveled around the country, you have a lot of hills, you have a lot of rain, and we know with these steep roads that you have a lot of landslides. So I just wanted to bring back the most recent one from Medellin that unfortunately caused death as well, destroyed homes. Other form of geohazards that geophysicists can tackle are liquefaction hazards, so ground motion effects on soils that are wet. This is the 2011 Christchurch earthquake that caused huge damage for the country itself. This was an earthquake that was close to the city, but it was close to a city with very wet soils. And that led to really immense damage, both in terms of casualties, but in economical loss. Of course, we think about geohazards as volcanic eruption. Closer to my home was the Mount St. Helens 1980 eruption. Also happened in the near-surface environment, a really powerful expression of dynamic Earth that caused casualties, damage, and if they were to happen today in the United States, it will be a tremendous damage. What unifies let me bring last point that is also relevant to you, is thinking about floods, flash floods, long-term floods, that are also the relation between the water content in the subsurface and the rainfall. And they also are what I consider geohazards. This is an example of a flash flood in 2025 in Texas that killed a lot of people and children. So it was very shocking to all of us and caused a lot of damage. And what that brought back to the community was the question on whether or not we could anticipate, predict, and alert these hazards. So a lot of the news were thinking about, was that a surprising effect? How good was the forecast? And was the science not just there yet? They were forecasts, but they were not listened to. But I think what these events are showing is that the community, the population is becoming more aware that I think we could be able to understand this hazard, and maybe we should. what I really like to think about geohazard coming from a seismological standpoint is that all of these flash floods, droughts, wildfires, earthquake ground failures, eruptions, or landslides, they were all unified because they all happen in the soil. The soil, I call that the subsurface environment, that is the sponge, that is that buffer between the atmosphere and the solid earth. But this is where we grow plants, this is where we live, we build infrastructure, and all of its integrity is that is what we rely on. And another interesting aspect is that soil unify the climate science and the geoscience, the solid earth geoscience. And there's an interesting coupling that we're exploring on whether or not climate effect can influence also the geohazards. So this is my quest. As a geophysicist, I think a lot about, we think about the subsurface. Deep earthquakes are one that are very prominent in Colombia, but all of the hazards that presented have an imprint on the soil, or they occur because of phenomena that happen in the subsurface. So coming from a very deep, triggering process for volcanoes, maybe 20 kilometers, all the way up to the 1 meter of soil in the canopy for the wildfires and maybe the droughts. And we sit above that. We live on top of that. All of these hazards have processes that are governed by the integrity of the subsurface. What's fascinating from a data-rich domain is we have the opportunity to see and explore these landscapes with different data sets. One that I'm thinking about is satellite imagery, especially when you think about wildfires, maybe landslides and floods. These are visible from from above the surface. And there are nice spatial resolution images you may get from this data. Nowadays, we have about 200 or more petabytes of these data. It's really vast data sets. However, they don't see the subsurface, and they may lack the spatial temporal resolution that geohazard occur on. So to bring this to the subsurface, the terrestrial network, the geophysical network, that amounts to a few petabytes as well of data, are an avenue for us to sense the subsurface. They don't have a good spatial resolution. Sensors are about 10, 20 kilometers, but they have a very high temporal resolution, which allows us to investigate processes, dynamic processes of geohazard. So I think a lot of the scientific question that we can address by verifying this data is thinking about how predictable, how susceptible these phenomena are. And I'm trying to think about earthquakes as being the least predictable and least visible, and maybe the drought being the slower to develop and maybe the most visible. But in that spectrum, I think we have opportunities to make progress. AI has been used to monitor volcanoes. So now I will go through these. The volcanic system is, I'm a seismologist, earthquake scientist, so I'm learning about it. You have experts here, but there's different ways that we still do not understand how volcanic eruptions occur and the different styles. Machine learning has been used there to monitor changes in sensor data. And they were used mostly, a lot of it was from seismic data, and they used techniques like classic machine learning, and maybe some small deep learning. But what they have been showing is these precursory signals in these different data streams may help us forecast the next eruption. A lot of these demonstrate as well, volcanoes are instrumented with very different data sets. They have, of course, geophysical seismic networks, geodetic networks, but they also monitor gases and infrasound and fluids and inflation. And so these are complementary data that can help inform the forecasting potential. Another way that AI has potential to support characterizing this research is by data mining existing data sets. So what we did in my group last year was my most fun computational experiment of my short career. We mined about 1 petabyte of data, seismic data, by mining I mean that we analyze every day of this continuous seismic record, and we detected earthquakes and surface events and explosion. And we did this over a petabyte of data. All of it is hosted on a cloud infrastructure on the Amazon Web Services S3 storage. And because we have a vast storage system and a lot of computing power to it, we're able to do this in almost a day of compute. And what we found from our data, we could detect some of these earthquakes and potentially detecting over 4 million earthquakes, which actually for some seismic networks, that's reasonable. But we have a very global view. A lot of the potential for discovering new science is going to be mining these new areas, these temporary networks that structural seismologists will spend time to go and deploy. So I'll show you what the type of detection we can do. These are the signals that we study, that we detect from. When we look at this data, the AI will also try to read a structure in this time series. So this is an example where we're doing a event classification. We designed a deep neural network, it's very simple, to discriminate if data comes in here, it will put in the earthquake category. If a waveform comes in here, it will put it in the explosion category. And if a waveform comes like this, it will be put in the landslide or surface flow category. But what it does, the AI does, is just it finds ways to recognize and put these waveforms in bucket, and it will look at things like impulsivity, strong and short signals, diffuse wave field with no transients, or maybe a strong coda. These are the features that we have interpreted as experts, and we understand how to do it ourselves, but the AI will map that understanding with maybe a bit more broad perspective on this type of characteristics. So this is showing you what deep learning is. So this is the black box open. We often think about data comes in, it's often normalized. We tend to think in temporal and frequency domains. This is spectrogram. And there's two categories of deep learning that are used for this time series. The one on the top you see here is what we call classic ML. And these are things like features are engineered. We pre-compute them, and there are a toolbox you can do that with. We can do a feature selection or feature dimensionality reduction with PCA. You probably heard that technique before. And then it comes in these ML algorithms like super vector machine, random forest, and whatnot. Then we can do the classification. So this is the branch of classic machine learning that is often used for this time series, and the volcano seismology uses a lot of this. The other branch is the deep learning algorithms, and they're effectively just filters. They are linear operations bundled in nonlinear functions, but they're just numbers, scalars, and biases that you optimize for. But they look like this. If data comes in with 1,000 points, it will then say, I will just project it on a different space, meaning a different set of vectors, and I will change the, it's a different transform. It's kind of like a wavelet or Fourier transform on different frequencies, but now it's a different, more general transform. And then what it does, and instead of calculating these features yourself, it will do it for you in this optimal way to classify between earthquake, explosion, noise, and surface event. And so this is AI for data processing. It's actually pretty simple. So I'll switch now to where we stand in AI for landslide modeling. And I want to bring this because it's an interesting paradigm. That there are studies that show that if we do AI to forecast landslide in purely data-driven way versus in a purely physics-driven way, all of these ingested interesting parameters that we think as scientists might matter, like planet curvature, DEM, slope, rainfall, all of these are data that we can ingest and make these forecasts. But each of these approaches, if you're purely data or purely model, you're not going to have the right answer. The purely data is a narrow view in the actual what happens in the world, especially for extreme rare events. We don't have enough examples of these. And the pure physical model lacks the physics that we don't understand yet. It's a physical model that is under-predicting, a physical model that is lacking some higher order processes like soil. And so often this balance between the two, you can see that the enrichment goes with joining the two, data and model together, and AI has methods to do that will really help, and this is demonstrated here, improve the forecast. Another aspect where AI is helping, AI and physical model are helping forecasting this hazard. This is taking an example of earthquake hazard, where we're trying to predict the intensity of shaking. On the left here, you have a purely data-driven approach, where in Japan, they ingested the waveform of the earthquakes, and they predicted the future shaking intensity, pre-ground value of, I forgot if it's acceleration or velocity, ahead of the shaking time. So this is a way to forecast the damages once you detect it, maybe with AI, you can forecast the intensity of shaking. And this is a purely data-driven approach. Once we start joining in physical models, here we're using, this is a paper from Lawrence Livermore, where they use physical models to not just predict the shaking value, but the full wave field in between sensors. So AI trained on simulation is able to not only just predict the intensity, but also the full wave field at the sensor and everywhere else. And so we're getting to move away from pure peak values at sensors to something that is very physical, full wave field with the sensors and the peaks. If you're interested also in floods and droughts, Google is doing a lot in flood forecasting. They're purely data-driven, they like the physics, but they're flashy in the sense of being trendy. Where they have quite good progress in 2024 because they have a lot of data where they use only rain gauges from rivers to then forecast the floods. And it's okay. It's not, it used to be improved, but it was a great breakthrough back then. Droughts are also seen in AI as potential. These are all the potential methods in AI, so in then artificial neural network assembling and decision tree, all of that are used to predict future droughts. So in a few minutes, I wanted to pitch you something that is a little bit more inclusive for them all. I really like the idea of AI enabling this interaction between climate, oceans, and geohazard. And we at the UW just got this small project funded. We were trying to understand how extreme rainfall that causes a lot of the landslides and liquefaction hazard potential we have in the Northwest actually originated from atmospheric failure that was generated by ocean-atmosphere interaction in the tropics. And this is because of that coupling that we ended up in last December with dramatic floods in Western Washington. What I find interesting in thinking about climate change or extreme weather precipitation is we often characterize seismic hazard as stationary. The only thing that changed is the occurrence of earthquake. And these are the maps that show the future likelihood of strong shaking. But we know that the climate is changing to such that we can anticipate potentially extreme rainfall and mean rainfall over the next 50 years. These are not yet incorporated in these kinds of hazards. We have detected with satellite imagery the sinking of the coast, subsidence that also compacts the sediments unevenly on the coast. That can be also transferred to understanding, given the sea level rise and the subsidence, we have an increase in flooding hazards and liquefaction potential as well that can be anticipated by understanding subsidence, future sea level rise, and flooding hazards. And so what I find very interesting today is by joining those data, models, and AI, I think we will be able to anticipate and forecast these hazards. I like to think about bringing on the big data, these petascale archives of seismic networks, geophysical networks, satellite imagery, smart systems. We listen to the Earth breathing in real time, and AI is good there for using the data in a multimodal and maybe characterizing these events. And then step will be assimilate the data and monitor how the soil is changing due to the rainfall and land management. And eventually bringing on physics-aware models, so physical models. If they are slow to run, we can have an AI surrogate model that then will help us forecast these hazards. And so this framework, if you're like all into GenAI, this is a slide for you. This framework of transforming our Earth system science into a digital twin is what I just demonstrated as a possible pathway. But we're also exploring how there's a new kind of data that I call scientific literature, text data, images, graphs, that can be used using agentic tools to augment our knowledge and prediction of this hazard. And so we at UW are developing agentic, little AI robots pipelines to help us orchestrate these workflows, but also learn about the interdisciplinary potential in geohazard and climate science. And so this is where I live now. We have volcanoes, we have coastal town, we have urban environment, we have active faults, we have a lot of hazards that can be problematic for this population. And so what I'm very optimistic that AI can help us, but really thanks to physical grounding and good data that will help us understand and forecast these hazards. Puget Sound is a small region, but including Seattle, but it has a bit of everything in it, and so I found a good natural place. However, I would love to do that in Colombia as well if we could collaborate. Thank you so much.
Vamos a hacer una ronda de preguntas sobre si alguien tiene una pregunta. ¿Alguien tiene una? No.
Are you already in the stage of integrating that with the government, for example? Because right here we have the UNGRB, which is the National Disaster Risk Management Unit. I think that would be really helpful.
Yeah. So the research that we're showing is very upstream. And usually governments wait for a few years, this is like recorded, wait for a few years to have consensus of the community in order to adopt this. But there's great potential to translate these basic research products of landslide susceptibility and liquefaction potential directly to the urban environments. And doing these translations, I think, are becoming increasingly easy with generative AI tools that help us scientists understand what the other users want. And so I think there's a nice pathway forward that will be faster to translate basic science, which is what I showed, to something that would be more ready for the government.
I've seen that in the United States, I want to talk about, for example, water management. I remember I have seen that they have some areas that are very low, limited with electromagnetic projects to, for example, follow every day the pattern of the soil. Because if you have the physics of the soil, there are many questions and many variables.
Yes.
That has to be documented.
Yes, the soil is so hard, and we're still struggling. We're building this model of the soil, but getting even the plain satellite product for soil moisture are not sufficient, and not sufficient spatial resolution that geohazards. I heard the human scale, the 100 meter to 200 meter scale. They are not yet sufficient to characterize that. The idea of repeated surveys to help monitor would be great. Brad will present on fiber sensing that I think has an opportunity to do real-time sensing. Resistivity, I'm not yet familiar with a permanent network that we would have for that monitoring. We just had a paper last week published that demonstrated that short-term dynamics such as evaporation and rainfall can occur over minutes and really change the soil characteristics. So I'm also pushing this idea of real time, small spatial scale, because we detected ET effects on soils within an hour. And so I feel like this is going to be an interesting challenge for us to think about soil as the ultimate hardest problem we can see, though. That's the thing we can tackle because it's right beneath our feet. So that's what I like about an actionable path forward is we can touch the soil, but it's a very challenging environment. It brings this cool like climate and agriculture and geotechnical, and it's just very, very attractive.
Thank you for you have a small example of a agent. Which one are you using?
Oh, yes, so we have one that detects, I don't have the demo right here, but it's one that detects earthquakes using these AI tools. So what I showed on deployment on the cloud, we have one that does it with QC, with network analysis, and does the full catalog pipeline. So no, we do agents are like not. It depends on the task.
Okay.
The computer scientists spend a lot of time in evaluation. And so when we make an agent, it's very easy to create a chatbot. Or create an agent for yourself. Like it's just, I can show you, I love this stuff. But for the science and for the computer scientists, for this multi workflow, scientific, so literature synthesis, hypothesis generation, data processing, data interpretation of the results. These are different research pipelines for us scientists that we do, and each of them requires a specific evaluation set that computer scientists will want to see in order to be, and I think scientists for that too, to have a research pipeline fully automated, but in a way that I like to think about the human centered AI that we can augment and accelerate our own science with these tools. My dream is to have just we chat and somebody like AI listens to us and run the analysis of the questions that we ask. And I think we're not far. I think we're about 6 months to 12 months away from doing that. If you like Claude, I have the prototype.
And which model are you using?
Yes, these models move fast, and all the base models advance fast. I'm more into Claude right now, but the most important is the gradient of physics, the context, the scientific literature that is used to generate the answer. Our papers are the most important. Our physical models are the most important because these are the ones that will avoid any hallucination and will really advance the science. So we have so much power because now, okay, the base models are improving, but really what will make them useful is us. We need evaluations from experts, we need good papers, reproducible papers, transparent language in our manuscripts, because they are used to generate these AI agents. Right.
Thank you.
Yeah, I have a question. So I have always thought about AI like a black box. So you have no idea what is happening in that box.
Wow.
Do you guys now understand better the algorithms that are behind AI?
Let me see. Yeah, I might try and move forward. This to me is the AI for processing. And I understand that these are, imagine a Fourier transform, where you project your time series on a different set of Fourier, and you get final coefficients. Now imagine that this transform is general. You optimize for the right decomposition and transform that match the goal, the objective, the target is this classification. So you're effectively building a transform that is specialized for your task. That's the supervised learning. These are decision boundaries found between different points, so different methods. For the generative AI, There's a lot of transparency when you look at chain of thoughts and what they generate and their workflow. And you can actually analyze the chain of thoughts that is output by these AI models for future purpose. But a lot of, if you have the right context and you as an expert see the answer, the black box is, it's all these units and transformers, that's fine. But the most important is that your input and output makes sense. And that the context engineering, the context that you bring is what will control the output.
Yeah, that leads to my next question. Because if you look at the seismological data of all these waves and all these functions with different amplitudes and so on that are changing through time, how do you know that what is recognizing the AI is real?
Yes.
Are you proving that against a new hypothesis that is not?
Okay, so the hypothesis I would have that a separate question. The scientific hypothesis is not directly from the wiggle processing, I would say. On the wiggle processing, a lot of the detection at single sensors is dubious. So we often have to, there's a lot of fault detection. So you often need other sensors to validate. But there's also another way to tackle this fault detection is by doing ensemble methods on the deep learning models themselves, because they will bring a consensus at the end. And they can be trained on different part of the world, different types of events. And in a way, with this different perspective, you get a distribution of answers. And with some statistics, you can decide on what's the right one. But it's computationally slow, because you need to load all these models in memory, and it gets slower. But it's much more conservative as an answer. For the hypothesis, this is more of a creative thinking. And a lot of this pattern recognition in the text that we wrote. So we need to write well, because all of the patterns that are found in our papers is just recombination of potential words together that then maybe generate new hypothesis. But it's what we wrote that the AI is finding. It's an interpolation of our knowledge. And I think what they can do with creating hypothesis from Gen AI is just interpolation among all of our different disciplines. It's just finding holes in our knowledge. It's not extrapolating yet. I think once we fill that interpolation map, then we can start extrapolating. Yes.
Yeah, because that's interesting that the slide what was showing where AI is basically data based, right?
Yes, data first.
And is very the predictions that are more based on physical modeling, phenomenos,
Yes.
parts of information. If the AI is not quite there, why it's not quite there? What am I comparing?
I think developing more training data sets from simulation, physics-based simulation, because then we understand. So like a machine learning algorithm that's trained on pure data will just interpret it within the data space. We can enrich that learning with physical models, in which case we can create new scenarios that were not seen in data to help extrapolate. If it's just using physical models, it's a surrogate of your physical model, which can be nice. One of the simulations for this quality earthquake, 3 weeks to run from the USGS. We don't have time. 3 weeks. What if we want a raw source model? We want 1 second. So surrogate of that physical model is also a valuable, goal. But from physical model to in the data, that's the enrichment space that we need to be crafting. So there's a lot of, we can control the data. We can control the question and the domain space that we want to sell. And we can do some on the architecture, but we can let also the computer scientists just go ahead and adopt what they have. Okay, fiber sensing.
Yeah. Sigamos el tema de gas.
And thank you for your question.
That yellow numbers? Is that yellow numbers?
This is the top.
No, no, I know, the yellow. Is
Oh.
Así,
Dale compartir a la presentación.
Oh, can you share?
¿Y lo vas a presentar? ¿Lo vas a presentar?
No. Sí, bueno, sí. Ok. Entonces, Brad Lipovsky es, no sé si es sismólogo, pero es glaciólogo, hace cosas bien diferentes. Por ejemplo, los barras diferentes. Tenemos que todos los conocemos en el Stanford hace muchos años, todos son más o menos sismólogos los físicos, pero cada uno se lo toma diferente camino. Entonces hice el doctorado de Stanford, después de un par de años, después de ser asistente en la Universidad de Washington. Como ustedes pueden ver, tenía 3 hijos con María. Es un niño, y están aquí, es corrupción de Colombia, los ciudadanos, marcan cuenta de uso de la educación física. ¿Listo?
Muchas gracias. Thank you for my talk about fiber sensing. And this talk, I'm not actually going to talk too much about the fiber sensing. It's in a lot of the different parts of the talk, but I think for the most part, I'm just going to think about distributed acoustic sensing and talk about it as if it was a bunch of seismometers. And I'll talk about distributed temperature sensing, but we'll just think about it as being a bunch of thermometers. So I don't think there are any glaciologists here. Are there? No? Good, that's good. This talk is for you then. So why should we study glaciers? Well, there's 2 big reasons. One is that glaciers are sedimentary rocks. They form from the deposition of material that compresses, snow that compresses into ice. And since they're sedimentary rocks, they record their own history. They also record Earth's history. For that reason, glaciers tell us about the history of the past, about our own history on Earth. And the other reason is that glaciers affect the future. They're part of the dynamic Earth system. And so for that reason, they affect things like habitability and geohazards, sea level rise, for example. So the outline of the talk is that we'll talk about both of those things: geophysics for the study of Earth's past climate, and geophysics for the study of Earth's future. And the 2 places we go for this they're just about as different as 2 glaciers can be. We're going to go to East Antarctica, which is cold and stable and hasn't changed in millions of years. And we're going to go to Greenland, which has a glacier that we're going to study that goes into the ocean that's changing very quickly. And in Antarctica, it's minus 60 degrees C, very windy. In Greenland, you do field work in a t-shirt, it's sunny, and you bring sunscreen. So it's very different. So this is a piece of ice from Antarctica, and it's remarkable because it has bubbles in it. And this is how glacier ice is different than the ice cubes that form in your refrigerator. Glacier ice forms from snow, and when it forms as snow, it's maybe 10% water and 90% air. It's very fluffy, and you press it, make a snowball. And so those bubbles don't go away. It starts out as a snowball, and it gets more and more compacted, and eventually it gets to be mostly, so the water, the density is very close to the density of pure ice. But those bubbles don't go away. And those bubbles have tiny samples of the ancient atmosphere. It's a direct sample. It's not a geochemical proxy. It's not something you have to kind of do an equation or a model to figure out what it means. It's a direct sampling of the air from when the ice formed. And it just so happens that this is one of the oldest pieces of ice that humans have ever touched with their hands. This piece of ice is probably about 6 million years old. It was recovered a few weeks ago in, a few months, 3 months ago now, in the Allen Hills of East Antarctica. So the basic way that we look for ice cores, so ice cores are, you drill down, make a borehole, you pull out the ice. And usually you look for something like this. This is the previous place where we had the oldest ice on Earth. It's from Epica Dome C. It's one of the summits, one of the peaks of Antarctica. And you look for something that looks like this. It looks like a bunch of pancakes. Or, I don't know, in the US we say a stack of pancakes. Maybe we say a stack of arepas. No, is that what? We make stacks of pancakes. So it's like, a lot of layers, or like pages in a book. And ideally, historically, what we do is we look for the places where it's very, very simple. Because you can basically just do layer counting. If you want to know how old the ice is, you just start at the top and you say 1 year, 2, 3, 4, 5, 6. You can count all the way down to the bottom. And you don't do it, you don't count with your hand. You can use a computer, you can do things a little fancier, but it's basically just that. It's basically just layer counting, 1, 2, 3, 4, 5, 6. And that's fine, but we've basically done all of that in the good places already. And it turns out you can do a lot better. I'll get to that in a minute. But the basic story of this is worth emphasizing. So we learn a lot places like this. The basic story that you get is that there were ice ages. So this is looking at the chemistry of the bubbles in the ice as a function of age, just doing layer counting. So we have really good absolute age control. We know exactly how old these samples are. And we can just look at CO2 and CH4, methane. But we just focus on CO2. And what you see is that there's ice ages. There's times when there was high CO2, and then this is actually temperature, which is from a proxy. It's from the delta O18 in the water ice. But just think about it as temperature. So what you see is that there's about here 8 ice age cycles. They're about 100,000 years old long. It takes about 100,000 years to go from an interglacial to a glacial. There's a temperature change of about, the big temperature change here of about 12 degrees C. And that's great, right? So this is like a fundamental thing that we learn about the Earth, that for the past 800,000 years, we had these 100,000 year period ice age cycles. Great. So the problem is that there's a lot more of Earth history that we want to know about besides just the last 800,000 years. The big thing being that at about 1 million years ago, the ice ages were shorter. They were only 40,000 years old, and we don't really know why, or at least about 10 different glaciologists will give you 10 different answers about why. So we need more data. And also, if you go back even further to the Pliocene, there weren't even ice ages. Earth was warmer, there was higher CO2 in the atmosphere, we think, and or at least that's the kind of standard story. To that in a second. But what you see here is this interesting trend into the beginning of the ice ages, right? Starting about 2 million years ago, we had ice ages. Before that, there were no ice ages. It's just more consistent. And so we'd really like to have direct records of that. If we could have those air bubbles going through this whole period, we would really learn a lot about Earth's history. And so that's why we go here. This is the Allen Hills. It's the place where the East Antarctic ice sheet, this vast ice sheet, it flows into the Transantarctic Mountains, which is a rift-controlled region. It's kind of a good tectonic analogy is like the Rio Grande Rift in North America. And so the ice sheet, it's like the open ocean. There's nothing to see out. There's just flat horizon of ice. And this is right where it starts to come into the mountains. And so there's some really weird things that happen in the city. But we knew that the Allen Hills were special because of this rock and other rocks like it. This is a meteorite. And so the Allen Hills are a really good place to find meteorites. So before people ever started thinking about what was going on in the ice, we noticed that there's just these meteorites sitting on the surface of the ice, just sitting there. And that's pretty special. If you care about meteorites, they're incredibly valuable, they're incredibly rare. This one is particularly interesting because in 1998, the President of the United States, Bill Clinton, went on the national news and said that this meteorite was proof that there was life outside of Earth. Nobody believes that anymore, but for a while, people didn't believe that. So it's a funny rock for that reason, a funny history. I don't the feature you can't see it, but I think it was little microbes. You need a microscope to see it. So it's a kind of infamous rock for that reason. But the reason why these meteorites appear at the surface, I'll tell you in a minute. But to give one more piece of motivation, so this is now jumping straight forward to the results. So we have these boreholes, these ice cores from the Allen Hills, and they go back to 6 million years now. This is out of date, this is from last year. But we find something, first of all, extremely interesting. So we can get CO2. We can get atmospheric CO2 content going back to 3 million years. Going back to 6 is hard because the ice is all messed up. We can tell you more about it. But what we find is really important is that there wasn't that much CO2 in the Pliocene, but the Earth was a lot warmer. And so that actually has a really big implication. Like most people thought before this work that during the Pliocene, the CO2 would have been a lot higher. That means that there's more than one way that the planet can get warm. The planet can get warm because there's higher CO2, but apparently there's other ways that the planet can warm up. So I don't know, I think that might be bad news for us, that we could have warming from CO2 in the future and warming from other things. I don't know. But you know, this is the kind of thing that we're getting out of this project, right? It's really fundamental textbook, like this is like Earth Science 100, you know, intro level results about the history of the Earth. So all that motivates us to go in and do geophysics, because with geophysics, we can understand how to find more old ice. I think we're going to find 10 million-year-old ice in the next 5 years. And I've had somebody at Lipovsky, so I've got a lot writing on this. And the way that we do that is with geophysics. We also just want to understand, how is it possible that ice could be preserved for 3 million, for 6 million years? This is not a normal ice flow model. Like a glacier model, a model of Antarctica does not predict that there should be 3 million-year-old ice. It does not predict, like standard models do not predict that ice should be this old in Antarctica. And so we've got a lot of work to do. We can do geophysics and we need to connect that to models. So that's kind of what this talk is about. So the classic starting point is this 1983 science paper called Catching a Falling Star, Meteorites and Old Ice, is the paper that first linked the flow regime, the way that the ice moves, to the occurrence of the meteorites. And they kind of have this model that I call it the ski jump model. It's like you come down and you jump off and it shoots up in the air or something. But the idea is that the ice goes down, and then when it hits the mountains, it's usually the Allen Hills, it gets forced upwards. And the reason it doesn't go over the mountains is because it's so cold and so windy in this part of Antarctica. There's so little snow because it's a polar desert. The accumulation is probably on the order of millimeters per year. That the wind actually scours out all the snow, and you're left with this exposed blue ice. I'll show you a picture of it. It's really beautiful. Now, okay, so this is kind of that explains some stuff. I think it explains why there's meteorites there, because they constantly get pushed to the surface. Usually in the ice sheet, if you put a meteorite there, it will sink to the bottom, right? Eventually it will get covered in snow and go down. But here they come up. So, okay, it explains that. The problem is that it doesn't explain that the ice is really folded. And that's actually not at all what we think the actual ages look like. So the ages look all right. They get older as you go down. This is just depth and age. But when you zoom in on this bottom region, it's crazy. It goes old, young, old, young, old, young. So what happened is, usually you have newer snow on top of older snow, but then somehow it got folded so that the younger snow or younger ice is below the older ice, and it happened repeatedly. So it's all folded up, and we think there's maybe even some faulting, which doesn't usually happen in glaciers. It's very complicated, which is great. So we have a real good reason to go do geophysics, which is really all that we're really looking for, right? So a ton of people have been involved in this. These are the people that are kind of collaborators in the current project. There's been probably 2 or 3 dozen people who helped out in the field work over the last 6 years. This paper specifically, this talk specifically will focus on kind of some of the borehole measurements, but we have also, very importantly, high resolution ground penetrating radar, GPS, borehole temperature sensing, acoustic sensing. We have borehole instruments like the tilt meter. We do ice fabric analysis on the actual ice cores that come up to understand anisotropy. And we have phase sensitive ground penetrating radar to do interferometry using radar through the ice. So, start to show you what some of these results tell us about the flow and how to find more old ice. Basically, what we have here is this is what the Allen Hills look like in a map. I haven't actually showed you a map yet. And the first thing you see is that the ice is actually blue. So they call it a blue ice area, and it is actually blue. Usually glaciers are white because they have snow on them. But here, all of that snow has been removed. Beautiful blue ice area. And I'm going to show you a transect going through these boreholes here. If you remember, there's a little a ridge, like an island of rock sticking out. We call it a nunatak. That's the Greenland word. It just means a ridge of ice sticking out from under, or a ridge of rock sticking out from the ice. We'll talk about this nunatak as well. And we're kind of just on the front of that nunatak. The ice is coming in this way from the front, flows from that direction. And let's see. This is now looking a depth profile, and we'll just look at the top to begin with. And what we see is that the bed, this is just ground penetrating radar. It's the same thing like, does Columbia have a call before you dig so that you don't like break cables and stuff? I know like,
Yeah.
like, you know, ground penetrating radar, you know, it's commonly used in, GPR, it's used for tons of things. Turns out radar in ice is like amazing because ice has very, very, very low electrical dielectric contrast. And so at very low attenuation, so you can see through ice very easily with GPR. So this nice crisp image is what the rock looks like underneath the glacier. And you see that it's really steep. There's these steep hills, it goes up and down, up and down. And remember, the ice is flowing into the page here. This is the cross section, so it's going like this. You see it goes around these big obstacles. Again, this is 200 meters tall over, that's 500 meters. So it's extremely steep. It's actually, this is no vertical exaggeration. No, there's a little bit of there's a vertical exaggeration I can have a comment. Yeah, quite a bit. It's 500 meters there. That's what big is, yeah. Anyways, we go into these places with vertical dashed lines. These are where the boreholes are, and we see we can just take the temperature of the ice. And the reason we do that was, you know, first of all, like what you measure is that it's almost linear. It goes from the average surface temperature down to some temperature in the bed, and it's just in geothermal equilibrium. So the temperature profile is almost flat. It's in conductive equilibrium. So it's actually a very boring temperature profile. When you, however, look at small deviations away from that temperature profile, sorry, is that clear what?
No, but it's almost that, so it's like same.
Oh, it's sorry. Yes, it's like a linear profile. So it's cold at the top and warms up at the bed because there's geothermal heating. Yeah. So white is warm, black is cold. Or sorry, white is cold and black is warm. And then what we really want to get at is the flow. And so what we do is we look at the tiny difference from the straight line profile. When you do that, you see something like this. So this is on the order, temperature anomalies on the order of kind of tenths to hundredths of a degree C. So they're kind of, we usually say 10 millikelvin or 50 millikelvin kind of scale. And so what we see is that there's cold ice in it. And that's a really important observation. We'll explain in 1 second why. Slide about this. Yeah, okay, so the claim is that basically these two things are not consistent. The standard model has the ice flowing up, but the problem is that when the ice flows up, it pulls warm temperatures up, and you end up with warm ice in the middle. If you have ice flowing down, then you have cold ice in the middle. It turns out it's a little bit more complicated than that because the past climate also affects the ice temperature. And those two things trade off, but we've done the whole problem in detail. We actually solved the whole thermal balance model in 3 dimensions. It's consistent with flow and with a temperature dependent reality. We can talk more about all the modeling. But basically this is the claim, is that if you have the ice flowing, you have the ice flowing up, you should have red in the middle. If you have the ice flowing down, it should be blue in the middle. And so this is a kind of a basic thing that we learn about the ice flow from these temperature profiles. We're essentially using temperature as a way to understand the motion of the ice. So here's what I do think is going on. This is a cross section from one of our 3D ice flow models, and it's not along a flow line. So we have 3 components of motion, and we're kind of on a flow line that goes straight into the nunatak, this exposed ridge. And what you see is that the ice kind of comes in from the continent. So the middle of the ice sheet is up here. The ice goes around in kind of map view, but then right into the nunatak, it actually stops. So these dots are arrows that would be too small to see. So these are on the order of the big ones. The big arrows like this are on the order of kind of 2 centimeters per year. These are on the order of, let's see, these are about 1 millimeter per year. And these are going to be about on the order of 1/10 of a millimeter per year. So the ice basically stops at a rate of about 1/10 of a millimeter per year. It would take the ice over 1 million years to go this distance. So basically, what we think, and here's another way to see this: the ice is coming down from the nunatak. It's coming in from the ice sheet, and in the middle it stops. And so this has a name actually in fluid mechanics. It's called a stagnation flow. When you have 2 converging flows, cause them to stop. And so this is one way that we think the ice is preserved. The reason why we have the 6 million year old ice here is because basically this weird geometry happens where the ice just stops or stagnates. There's actually, so like I said, there's a classic fluid mechanics solution for this, and I did something called conformal mapping. So there's a solution you can do with math, with like pencil and paper math, that kind of captures this behavior. So the classic fluid mechanics is that you have 2 flows coming in like this, and they actually do something kind of like this. They spurt up, and then in the middle it stops. And I took that and I deformed the coordinates with something called conformal mapping, which is something that was invented like 200 years ago by a Russian mathematician. And basically you can derive a new fundamental solution in Stokes flow, which is nice because it's 2026, and it's not every day that you get new solutions to really basic fluid mechanics problems. This, of course, the simple math, it doesn't capture all the beauty and richness of the real problem, nature or a more complicated model, but it lets us understand some of the really basic pieces. So we have a bunch of other measurements. I'll just go through some of them. This is an amazing instrument. It's a very, very accurate tilt meter. So it tells you the degrees that you're tipped over from vertical in degrees or radians. Except that if you look here, the manufacturer's spec sheet, which is so amazing that I made it in pink, is it claims that it has 2 to the -10 radians of resolution, which if you calculate it, that's in 1 meter, that's the height of a carbon atom. I don't know how you could check that that's right. I think it has something to do with the noise floor, but I think it's like, I don't know how you can prove that that's wrong, because you can't make an actuator that moves that low. But the thing that I'm kind of proud of is that, so this slide is actually like 4 years old when I first proposed it. And I didn't change the slide because we almost predicted the right number. We're only wrong by a factor of 10 from what we actually measured. So we kind of predicted that we would be in the range of, what do we say, 1 to 10, or say 10 milliradians per day. And the number was actually closer to about 50 milliradians per day. And again, that's because the ice is creeping so slowly, we needed a really fast instrument. And as it creeps forward, you just get a little bit of tilt. And so we're able to use this basically as a kind of 4-hole GPS instrument, right? It's in 2 axes, so it tells us how the ice is moving. And we can do that even, at the bottom of the borehole. So it's a calibration point for our model, basically. We can use it as a way to check our numerical model. I'll say one thing. So all the modeling that we've done so far, it's just a snapshot. We're only trying to describe how the model is behaving today, how the ice is behaving today. We haven't done anything about, the real problem. The real problem is, how did ice change over the last 6 million years in order for it to be where it is today, in order for it not to have somehow floated off into the ocean. And so this is what we want to do next, but we can get a little bit of information. So we can get a little bit of information thinking about how the ice would have behaved in ice age cycles. If there was a lot more ice, or if the ice was thicker, how would it be different? And the reason we can do that is because at one borehole, the ice has this counterflow and it stagnates because the ice slows down because there's the nunatak that gets in the way. But here, remember what the profile looked like? The ridge dives down under the ice, and here the ice flows over. So it flows over this submerged ridge. And so I think this might be more like what it looks like when there's a glacial period where there's more ice, the ice is thicker, it's able to flow over the nunatak. And so what you see here is that now the ice is flowing down, and so this is vertical down, and then to the right, it's red. And when the ice is bigger, it flows up, goes over the ridge, and to the left. And I think this is again just speculation because we haven't actually done this, but I think this is why you get folding. I think if you oscillate between going down to the right and up and to the left, that you could make folds. So that's one idea about the origin of fold and kind of the stratigraphic complexity at this site. I only have one more thing. I can just do this part. I actually have a whole other part to talk about. If people want to stay, we can do more, but we can wrap up this part. So this is, one of the results. We basically see that in all the boreholes we have, the age is correlated with the speed. So we think that this idea that the ice gets really slow and it almost stops, it gets trapped in the topography, is really important for preserving the old ice. That the oldest ice we have is also it's the slowest flowing. But then there's this one outlier here, which is strange. And we spent a lot of time thinking about this. We were writing a manuscript and we couldn't really explain why it was so different. We just thought in our heads like, okay, 6 million years, or we'll find that one's 5 million years old. A lot could happen in 5 million years. It must just be like a different glacier came from somewhere else. And it has a different age just because it's a different glacier. You wouldn't expect the speed to predict everything if you have different glaciers with different material and different ages coming together. So there's some different kind of story. It could have gotten old somewhere else and got brought in, and versus the other ice in the stagnation zone got, it came in and then got old while it was here. And so it turns out that the geochemistry supports this really well. And this is all totally new stuff for me because I'm not a geochemist. But and the idea that this site is geochemically totally different than the other sites. And so this has led me to understand a lot more about geochemistry than I ever thought about, a lot of stable isotope geochemistry. So the quantity I'm plotting here is deuterium excess, which has to do with kinematic fractionation. So it has to do with where the water came from that eventually formed the snow. And so what we think is going on here is that we have two different source regions, two different glaciers, right? So these sites, they're all moving really slowly. We think the ice came in and just stopped, and it hasn't moved in 6 million years. It's been, maybe tens or hundreds of meters away for that entire time. Kind of amazing. This ice is moving a lot faster. We think that in the same amount of time, it could have moved 50 kilometers. It has an isotopic signature also. There's a bunch of other things we can plot, a bunch of other proxies, but it has this isotopic signature of coming from higher up in the ice sheet. So we think that these are all relatively the same elevation where they are now. This one is moving faster. It came in from higher up on the ice sheet and it got stuck where it is today now. So it's cool. We can actually work out with the kind of combination of geochemistry and the flow modeling and the geophysics. We can work out these different modes of preservation. We see there's not really one story. There's at least two stories about how the old ice is able to exist. Okay, that's basically that. I mean, should I wrap up there, or do you want to see the whole thing?
Yeah.
Do questions? All right, I'm happy to wrap it there. So.
So what would be the alternative explanation for the warm temperatures? Biology,
Yeah, the opening of the isthmus, or the closing of the isthmus of Panama happened. I think that was Miocene. So I don't know. There's like big changes in ocean circulation. Honestly, I don't know. Yeah, again, like you always like put the claim on the part that's not what you study. Yeah, so, we didn't study ocean circulation at all, so maybe it was the ocean. I don't know. I mean, it's getting to be long enough that there's big changes, right? Like I know that in earlier times, the paleogeographic changes could be invoked. I'm not totally sure. I mean, there's a bigger trend of Cenozoic cooling, right, over like 60 million years that was related to closing of the Tethys and subduction of carbonates like this, but not sure. Yeah, I don't know. It's a good question. Yeah.
When you showed the modeling, the flow modeling, that was the type of size of the beginning. to that.
Yeah.
And I was thinking that the same model has been suggested for a confirmation mountain, right?
Yeah, like critical taper theory, yeah,
Yeah, so no, but also coming up.
Oh, like an exhumation.
Then coming up
Mhm.
and the extreme. So I was thinking about explaining so you were measuring the velocity of the flow relation, right? But then your instrument was already snow. So how representative of the whole block of ice can you measure the flow on this snow if the ice becomes further to the bottom? Do you know what I mean?
Yeah, it's a really hard problem from like a measurement perspective, because it's the flow is truly three-dimensional. There's no cross-section that captures all the behavior. It's moving horizontally and vertically in different ways. And so it's hard to get the coverage you need. There's a lot of stuff in our model that is not validated with data. We do have a lot of boreholes though. So we have, because the ice is only 200 meters thick, and you can drill with, if you don't care about getting the ice core out, you can drill that much in a day. If you care about getting the ice core out, it takes like 5 or 7 days to drill 200-300 meters. So we have a lot of boreholes. And so we can use the tilt meter, and then we can use this indirect measurement of measuring the temperature and essentially isolating the advection component. So we know very well what the conductivity is of ice, and so we can back out the conductivity signal. And then we also have to remove a common mode due to atmospheric warming over the last 200 years, which I didn't talk about at all. So we also have to account for that. And there's a lot of uncertainties in that, but even with all those things considered, we can still use it as a bound on temperature. We actually thought it would be a much bigger signal when we first proposed this project. We thought we would see a very big signal based on the surface GPS velocities. But we didn't understand the stagnation. It turns out that we're going to an area with extremely low velocities. So the advection signal is a lot smaller than we thought it was. And it ends up being bound. The advection that we measure is bound on the ice field velocity. Yep.
Then the shorter to the temperature or normal velocities, that's.
Oh no, I think they're in agreement.
Okay.
Yeah, we have the normalized fit to the GPS velocities. It's like on the order of a few percent. I think we can fit the GPS. It's like 5 or 10% standard error.
Thank you. So then,
Yeah.
maybe the proposal experiment test and the specific piece of this possible. Let's intro and send us.
Yeah. Yeah, and it'd be fun to think about getting like an outcrop scale in geology. I don't know how much it was totally out of my field. Most of like the geodynamical modeling that I know about is very big scale. It's like subduction zone scale. But this, is very small scale even for ice flow modeling. Like we have a 1 meter grid spacing. So it's just you actually get to the point where you're like modeling, that'd be like modeling individual outcrops. Better different. Yeah.
¿Más preguntas? Pues agradecemos a Marina, ¿verdad?